A random variable is one that has at least two possible values, and in advance, you don't know which value you're going to end up with. There are generally two types of random variables, discrete and continuous, and those two types are differentiated by how many possible values there are. A discrete random variable, which usually is a count, can only assume a finite number of possible values or a countably infinite number of possible values. The way that you would get a countably infinite number of possible values is if you have a count where there's no highest possible value. A continuous random variable is one that can take any value in some specified interval. Realistically, these are almost always physical measures, things like distance, area, volume, weight, and so forth. Time is not a physical measure, but the way that time is measured is analogous to things that are. To identify the discrete variables, the important thing is to be able to pick out which ones are counts. Granted, the phrasing of A and D is identical, starting off with the phrasing number of. It doesn't always have to look like that. There could be different words there, but the main thing is that both of those are counts. B and C are both continuous, B being a physical measure and C being time, which is handled like a physical measure. A discrete probability distribution, especially one with a finite number of possible values, can easily be arranged in table form, where you would have a list of the possible values of the variable and then the probability associated with each value. These two statements have to be true for any discrete random variable. The probabilities of all values are going to be non-negative, so you can't have a probability less than 0. The other thing is that all of the probabilities have to add up to 1 because one of the possible values has to occur. Here we have a discrete probability distribution listed in table form in that blue table toward the center of the screen. There are 4 possible values and then 4 probabilities, one going along with each of those possible values. If X is the number of times that a randomly selected student takes the SAT, we can figure out probabilities like the two that are listed on this slide fairly quickly just by adding probabilities of individual values together. To find the probability that X is greater than or equal to 2, we just have to add up the individual probabilities of the values that satisfy that inequality of being greater than or equal to 2. The 3 values that would satisfy that are 2, 3, and 4. If we add their probabilities together, we get 0.52. To find the probability of this compound inequality, we need to include the 1 because there's a non-strict inequality there, but we need to leave out the 3 because there's a strict inequality there. The only possible values that satisfy that compound inequality are 1 and 2. If we add their probabilities together, we get 0.88. The expected value, or mean, of a random variable can be computed using that formula that's on the screen. If you look at what that formula really is, it's a weighted average of the possible values of the variable using the probabilities as the weights. That will give you the expected value. We're going to find the expected value for the SAT example, so the first thing that we're going to do is expand the formula while substituting values in. To find that expected value, it would be 1 times the probability that X equals 1 plus 2 times the probability that X equals 2, and so forth until we've exhausted all possible values. If we substitute in the actual probabilities, 0.48, 0.4, and so forth, then multiply 4 times, add those products together, we'll eventually end up with an expected value or mean of 1.65. We can also compute the variance of a discrete random variable. By definition, the variance is the average or expected squared distance from the mean. The formula that's in the first box is a literal interpretation of that definition, written symbolically. There is the alternative method in that second box, which a lot of times is faster. The expected value of X squared minus the expected value of X quantity squared. That's a variant of the first formula, just with some algebraic simplification done to it. A Bernoulli distribution is the simplest kind of discrete probability distribution. It's one with only 2 possible values, which generically are referred to as success and failure. Think of flipping a coin. That only has two possible values. If the outcome that you're interested in is tails, then that would be your success, and heads would be considered failure. Typically, success is denoted by 1 and failure by 0 when the probabilities are written symbolically. Some of the formulas that we're going to talk about later hinge on that, so we're going to use that convention. It's also customary to label the probability of success as P. Now suppose that instead of just one Bernoulli experiment, we perform several or perform the same one over and over again. So instead of flipping a coin once, we flip it 8 times. In general, let's say we do n repetitions, then the value n would be the number of repetitions or the number of trials, which is the conventional phrasing there. We would have a Bernoulli random variable for each trial, and if we label them using subscripts to denote which trial they correspond to, we would have x sub 1, x sub 2, x sub 3, and so forth up to x sub n. As before, we'll assume that the probability of success for any trial is P, and that that probability is consistent, that it doesn't change from one trial to another. At the bottom of this screen, there's a new random variable x that's constructed as the sum of all of the individual Bernoulli random variables. X, in this case, would be a binomial random variable. For each Bernoulli random variable, the possible values are 0 and 1. So the smallest possible outcome of x is 0. If there's a failure in each Bernoulli random variable, then you'd be adding a bunch of zeros together and you would get 0. The largest possible value is n, which is what you would get if they were all successes. If you had 1 plus 1 plus 1 plus 1, n ones added together, you would end up with n. And any integer in between would also be possible. So the possible outcomes of x, 0, 1, 2, 3, and so forth up to n. Therefore, x is counting the number of successes, because every time there's a success, that's when you add in a 1 instead of a 0. The entire purpose of this little piece of the notes is to illustrate how quickly the number of possible arrangements balloons. Suppose we wanted to find the probability of 3 successes and 5 trials. We'd need to know how many different arrangements there are of 3 successes and 2 failures. This one you can do by brute force, and it doesn't take too long to figure out that there are 10. But you can see how this would become a problem relatively quickly. What if we wanted to find the probability of 12 successes in 20 trials? Then you'd have strings of 20 characters with 12 S's and 8 F's, and you'd have to find all possible arrangements. That would take a very long time if you tried to grind that out by hand. Therefore, we need a quick way to figure out how many different ways you can have k successes in n trials. In order to do that, we use something called a combination, which is read as n choose k. The conventional notation is the one with the parentheses, with the n over the top of the k, although the one with the large C in the center is typically how a calculator would write it. The way that a combination expands is as a quotient involving 3 factorials. It expands to n factorial divided by k factorial times n minus k factorial. The way a factorial is computed, for example, 5 factorial would be 5 times 4 times 3 times 2 times 1, which is 120. 7 factorial would be 7 times 6 times 5 times 4 times 3 times 2 times 1, and so forth. By definition, 0 factorial is 1, not 0. This is the general formula for a binomial probability, or as it's phrased there, the probability of observing k successes in n trials. The n choose k is to take care of all of the different possible arrangements that you can have of k successes and n minus k failures. P to the k times 1 minus p to the n minus k, that's the probability of one arrangement of that number of successes and failures. Binomial probabilities are significantly less abstract with actual numbers, so there's a long multi-part example in here now. If we have a multiple choice quiz with 5 questions on it, each of which has 4 possible answers, there are several probabilities that we want to figure out. If a student guesses on all questions, then whether they get each question right or wrong could be represented by a Bernoulli random variable. Therefore, what they do on all 5 combined would be a binomial random variable. So these are going to be binomial probabilities with n equal to 5, since there are 5 questions, and a probability of getting any individual question right of 1/4, since there are 4 possible answers. First, the probability that they get 4 questions right. The 5 choose 4 will cover the number of possible arrangements of 4 successes and 1 failure. Then the 0.25 raised to the power of 4 times 0.75 raised to the power of 1 is the probability of each arrangement of 4 successes and 1 failure. Most of the simplification here is simplifying the combination. First, you can rewrite it with factorials. Then in the third bullet point, if you expand the factorials, you have a lot of things that you can cancel, and you end up with just 5 for that combination. And then if you multiply 5 by 0.25 to the 4th power, and then by 0.75 to 4 places, you get 0.0146. Next, we want to find the probability that they get less than 3 questions right. This one will take a decent amount of work, because less than 3 questions would be 2 or less, and we'll have to find the individual probabilities of all numbers of successes that are less than 3 or less than or equal to 2, either way. So we'll have to individually find the probability that x equals 0, the probability that x equals 1, and the probability that x equals 2. This slide shows the probability that x equals 0. The computation there is really quick. The first 2 components of that product are both going to be 1. Since anything raised to the 0 power is 1, so 0.25 raised to the 0 power will be that, and 5 choose 0 also works out to be 1. You can see it with the expanded combination into factorials. The 2 5 factorials would cancel, and 0 factorial by definition is 1. So all you're left with at the end is 0.75 to the 5th power, which is 0.2373 to 4 places. The other 2 are on this slide. We need the probability that x equals 1, so now k will be 1 instead of 0, so it'll be 5 choose 1 times 0.25 to the 1st power times 0.75 to the 4th power. Eventually that'll simplify to 0.3955. Then the probability that x equals 2, now k is 2, so 5 choose 2 times 0.25 squared times 0.75 to the 3rd. Eventually that will simplify to 0.2637. Notice that 5 choose 2 is the same thing that we got for 5 choose 3 earlier. They're both 10. But think about it this way. 5 choose 2, when you rewrite that with factorials, would be 5 factorial divided by 2 factorial times 3 factorial. So the only difference between 5 choose 2 and 5 choose 3 is the order of the factorials in the denominator, which doesn't matter because they're multiplied together. Therefore, they both simplify to 10. Finally, to get the probability that x is less than or equal to 2, we just have to add those 3 individual probabilities together, and we end up with 0.8965. This one could be lengthy, but there's a way to shorten it up quite a bit. If you do it directly, where the probability that x is greater than or equal to 1 would be equal to the probability that x equals 1 plus the probability that x equals 2 and 3 and 4 and 5, and then you add all of those together, that will take a long time if you don't have the individual probabilities figured out already. However, if you use the complement here, this is a lot shorter. The probability that x is greater than or equal to 1 would be equal to 1 minus the probability that x is less than 1. 1 minus the probability that x is less than 1 is really just 1 minus the probability that x equals 0, because the only possible value for x that's strictly less than 1 is 0. We already have the probability that x equals 0. We found it as part of number 2. It's 0.2373. So the correct answer is 1 minus 0.2373, which is 0.7627. So if you have a situation where it's a binomial probability and it looks like you have to add a lot of individual probabilities together, one thing that's worth thinking about is, would the complement be shorter? Because sometimes it's a lot shorter. The expected value and variance formulas that we have for general discrete distributions would work here, but they're not necessary. There are specific binomial versions that are a lot faster. For a binomial distribution, the expected value, or the mean of the distribution, is just n times p, the number of trials multiplied by the probability of success in a single trial. And the variance is n times p times 1 minus p. And if you wanted the standard deviation, you would just take the square root of the variance to get it. For the quiz example, we can get the expected value and the variance very quickly using those formulas, since we know that n is 5 and p is 0.25 already. The expected value would just be those two numbers multiplied together, and you get 1.25. The variance would be n times p times 1 minus p, so really 1.25 multiplied by 0.75, and you get 0.9375.